All right, we are going to start talking today about electric charge, which is going to lead us to talking about the electric force. All right, so we are starting with this figure from the textbook, and this figure is showing a stream of water coming out of a faucet, and nearby to the stream of water, there is this comb, and the presence of the comb is having an influence on the stream of water, and you can see that the stream of water, rather than traveling in this straight line like you would expect, the stream of water is actually curving. And so that suggests that the comb, the presence of the comb, is influencing the motion of the water. So why is the motion of the water changing? Well, now we need to go back to our 101 thought process and begin to explore and hopefully explain what's going on. So we know from 101 that if the motion of an object, in this case the water, is changing, then there must be a net force acting on that object. Now, the beam of water was traveling straight down and it's been deflected to our left, and so there must be some force acting to the left on the water as it's passing the comb, right? Because the beam of water has been deflected. Now, the water isn't actually touching the comb, and so we also know from 101 that we must be dealing with some type of long-range force. Again, from 101, the only long-range force we know about is the force of gravity, and we know that objects with mass will attract each other. And so I suppose the most obvious candidate for this phenomena is gravity. Is it the force of gravity that's causing this stream of water to deflect? And I've highlighted over here the universal law of gravitation. For two objects, mass 1 and mass 2, separated by a distance, then you can calculate the force, the gravitational force of attraction using this universal law of gravitation. And it turns out that if we ask, can this phenomena that we're observing here be the result of gravitation, the answer is no, it's too weak. And we're not going to do it right here, but in the next few classes, we'll start investigating that, and we'll start doing a few calculations that support that statement. But for now, just believe me when I say that the force of gravitation between the comb and the water droplets is too small, it's too weak to actually cause this change in motion that we're observing. And so all of that put together means we must be observing a new long-range force, one that is not related to the masses of the objects, right? And so the reason that I brought up gravity is because just like mass, right, leads us to talk about this long-range force of gravity, we have electric charge, which is going to lead us to talk about a new force. And in fact, this new force we're going to call the electric force. So when I say electric charge, what do I mean? Well, as you read in the book, over the course of a few hundred years of experimentation, physicists determined a variety of different characteristics or properties of this thing called electric charge. The first thing is that unlike mass, there are two types of charge. We, I suppose thanks to Benjamin Franklin, refer to the two types of charge as positive and negative, but that's a completely arbitrary designation. I've got written here left and right, red and blue, apples and oranges. Those all would be appropriate ways to categorize these two types of charge. So there's nothing inherently positive about the charges that we call positive. There's nothing inherently negative about what we call the negative charges. It's just two different types of charge. Right? And again, that's a significant difference from what we saw in gravity, because In gravity, there's only one type of mass. All right, so the symbol that we're typically going to use when we are talking about charge, the symbol is going to be a Q. So typically a small q for something like a point charge or a small object, and a capital Q for sort of a macroscopic object, kind of an extended surface. Typically we'll use a capital Q. And the unit that we use, the SI unit for charge, is the coulomb. Right, so this is our standard unit of charge, the coulomb. Now, charge is quantized. What do I mean by that? Well, what I mean is that there is a minimum, there's a smallest value of charge that something can have, and that fundamental unit of charge, script E, is 1.602 times 10 to the negative 19 coulombs. We're going to typically use 1.6 times 10 to the negative 19 coulombs. That is our fundamental unit of charge. And the last thing that I want to mention here about charge is that charge is a conserved quantity. So just like in 101 when we talked about energy and we talked about momentum, charge is a conserved quantity. That means the total amount of charge in the universe is always the same amount. We may be able to transfer charge from one object to another, but the total amount of charge remains unchanged. And then if you have a system, a system that you've identified, and say that system is isolated, well then the charge within the isolated system will always remain the same. Again, the charge could get transferred from one object to another within your system, but the total amount of charge is conserved. Now, over on the electric force side, I've got a few things to point out. Unlike gravity, the electric force can be both attractive and repulsive, or attractive or repulsive. And we are all pretty familiar with this. Like charges repel, and unlike charges attract. Right? So this is different than gravitation, because in gravitation we only had attraction. Now we have the possibility for repulsion. The magnitude of the electric force between two charged objects decreases as the separation increases. This is actually identical to what we saw with gravitation. Now, where do our charges come from? Well, there are a few different ways to answer this, but let me start by focusing on the matter, or the stuff that we typically interact with in the class or in our problems. Matter is made of atoms, and our atoms are made of electrons, protons, and neutrons. And so in this figure here, I've got a little schematic of a diagram for an atom where you've got the electron cloud, right, outside of the nucleus, and then you've got your protons and neutrons inside the nucleus. Now, the electrons are negatively charged particles. They have the charge magnitude, the fundamental unit of charge, but with our category negative. Our protons have the fundamental unit of charge with our category positive, and then our neutrons actually have no charge whatsoever. So taken all together, typically our atoms are neutral. That is, there are the same number of protons and electrons present. So same number of protons and electrons, the net charge of a typical atom is neutral. But of course, you can add or remove an electron. And when that happens, the atom becomes charged. It's no longer neutral, so it can become a positively charged or negatively charged ion, right? The term for that type of atom is an ion. Now, of course, there are other particles other than electrons, protons, and neutrons in the universe, and so I've just listed a few of the other types of particles that we may end up seeing in problems throughout the semester. And again, typically when those particles get used, they'll be introduced and it'll be explained what the charge or what the mass, any information that you need about that particle will be provided if the problem includes it. Okay, so we know what types of particles are making up our atoms, and our atoms are making up our materials. And what we want to think about now is that there tend to be two categories of materials that we will see and solve problems with in this course, and those are conductors and insulators. And you probably are familiar with this, but the idea that an insulator, it's difficult for charge to propagate or move or around, whereas a conductor charge is sort of free or easy to move throughout the material. And so the way that we can explain why there's two types or versions of materials is if we just check out the model atom that I've got here. Right, so this model atom shows the nucleus in the center, and then the electrons in the cloud around it, and then there's sort of this set of valence electrons. These are the electrons that are furthest out, essentially, from the nucleus. And what we find is that for insulating materials, these valence electrons are tightly bound to the individual atoms. And so what that means is that if you add charge to an insulator, say in this location over here, it is not able to move around the material, and the charge that you've added will essentially stay at the location that the charge has been placed. Conductors, though, are fundamentally different. It turns out with conductors, that valence region, right, it turns out that these valence electrons are essentially shared by the entire material, the entire medium, generating or creating what we call sort of a sea of electrons. And what that means is that charge is free to move throughout the material. And so this is sort of the fundamental difference between an insulator and a conductor, is the ability for charge to move freely. So it's not that charge can't move with an insulator, but it's just significantly more difficult for a charge to propagate through the material. Okay, so we've got insulators, we've got conductors, and now we want to investigate how or if it's possible to alter the charge of an object. So I'm going to start with this figure from the textbook, where we've got three different scenarios. We've got a positive rod being brought close to an insulator. We've got a negative rod being brought close to an insulator. And then we have a negative rod being brought close to a conductor. And so in each of these three cases, the charged rod is brought close but does not touch the other object. So let's go back to the left. So I've got a positively charged rod, and you'll notice what happens. My charges within the insulator, they don't move a lot, but they do separate. You'll notice the negative charges in those atoms are now on the left side of the atom, and the positive charges are on the right side. And so that means the left side of the material is a little more negative than the right side. The right side is a little more positive. Now, if we look at the second picture, we've got a negatively charged rod, and essentially the same thing happens, but now the positive charges are attracted a little more on the left, and the negative charges are repelled a little more to the right. But again, the total charge within the insulator has not changed. The charge has just moved or separated. And then all the way over on the right, we've got a negatively charged rod coming close to this conductor, and you'll see that here the positive and negative charges have separated significantly more than within the insulator, and that's because the charges are free to move. And so the positive charges are attracted to the rod, and so they're on the left. The negative charges are repelled, and so they're over on the right. But the key thing is that the net charge of these objects does not change. Why is that? Well, because there actually wasn't any contact. But something did happen. What happened? The charges moved, and we call this process, where you can separate or move charges while maintaining the total net charge of the original object, we refer to that as polarization. All right. Now, how do we actually change the net charge? Charge must be transferred, and typically to transfer charge, we need contact. So let's look at this figure down here that I've created to kind of explain one of the simplest ways to transfer charge. So in this first image over here on the left, I've got an insulator and I've got a negatively charged rod that I'm bringing in contact with the insulator. And you can think that, all right, I'm just going to slide the rod over the insulating object and then I'm going to separate them. So now I've separated the objects. And what's happened is that some of the negative charge on my rod has been transferred to the insulator. Now, charge is not free to move throughout or around an insulating object, and so that means the negative charge that's been transferred essentially stays in the location where it was transferred, right? It does not distribute around the object. And so when I end up removing the charged rod, I have a negatively charged insulator where the negative charge is located where I deposited or transferred the charge. So that's for an insulator. Now if we look at the example below that, I've got a conductor. Negatively charged rod brought close by and then brought in contact with the conductor, and then the two objects are separated. And what I've tried to represent here is that some of the negative charge on the rod has disappeared. Well, where did it go? Look at the conductor, and now I've only drawn 3 negative charges. Before, there was an equal number of positive and negative charges that I had drawn. And so this represents a negatively charged object now. And of course, after I move the negatively charged rod away, that charge distributes itself evenly over the surface of the conductor, and I end up having a negatively charged conducting surface. So this is a really important point. Objects that are charged in this manner through direct contact from the charging object, objects end up with the same charge as the charging rod. All right, and it's also possible to charge an object without directly touching the object with your charging rod. And this process is known as charging by induction. So let's look at what needs to happen. So in this figure that I've pulled from the book, the figure starts out with 2 conducting spheres that are in contact with each other. Now these are neutral conducting spheres, so I don't have any charges drawn on top of the spheres, but I bring, in the second panel, I bring a positively charged rod nearby, and even though I didn't draw charges in the top, there are charges there, and so when I bring this positively charged rod nearby, the charges separate. And so the negative charges are attracted to the positive rod, our positive charges are repelled, if you want to think of both charges as moving. And so I have essentially separated out the charges, right? I've polarized this double sphere object. Now, if I go down to panel C and I leave the positive charged rod there, so you can think of that positively charged rod as it's still attracting those negative charges, it's still repelling those positive charges. And during that process, if I move the right sphere away, remove the contact that it was making with the negatively charged portion of the sphere, all of a sudden I now have 2 separate spheres, one negatively charged and one positively charged. The important thing to point out here is that these conducting spheres are on these insulating bases, and so when you go to move this sphere to the right, you've actually got to do so by touching the insulating portion and not touching the conducting portion. So you separate the rods, and then after you separate the rods, you separate the spheres, and after you separate the spheres, you can remove the rod, and then you end up with two charged surfaces, one negatively charged and one positively charged. Now, in this last panel, the two spheres, the charges are sort of unevenly distributed on the surface, and that's because the two objects are near each other. If we move these objects significantly far apart, those charges then would uniformly and evenly distribute over the surfaces of those spheres. But an interesting thing to note, the object, and in this case, the object is I'm referring to as the leftmost sphere. So it's the middle object when I've got all three of these things here. So the middle sphere ends up with the opposite charge as the rod that was brought close by. Right, so this is the opposite of what happens in the first case that we looked at on the previous page. So here's another example of this process. I've got a conducting surface that's net neutral, and I bring a positively charged rod nearby. When I do that, the charges separate. Right, so negatives are attracted, positives repelled. Then what I'm going to do is I'm going to ground the sphere, and you can ground the object in a variety of different ways. The easiest way is to touch the sphere with your hand, right, to ground it. And when you do that, the ground you can think of as an infinite reservoir of positive and negative charge. And so when you ground this sphere, the negative charges over here, you can think of them as being held in place by the positive rod. But the positive charges over here on the right hand side, they are free to leave. Now, if you have a problem with the positive charges being mobile, then the other way to think of it is that negative charges flow in to the sphere from the ground and essentially mitigate that excess positive charge on the right hand side. And so now we remove the ground, so you remove your finger from the sphere while keeping the rod nearby, and now you'll notice that we only have negative charge on the sphere. Then we remove the rod, and we have a uniformly charged spherical surface. And again, this process is called charging by induction. At the end, the sphere is negatively charged. The rod that we brought close is positively charged. And so, again, the object ends up the opposite charge as what the rod was that was brought near.